Do you really exist, or are you just a pattern in the cosmic fabric of space-time? Have you ever wondered why objects fall toward Earth? We say gravity, but what if everything you know about gravity is fundamentally wrong? What if space and time aren't what you think they are at all? In this video, we'll explore Einstein's revolutionary concept of space-time, the living, breathing fabric of reality that completely transforms our understanding of the universe and our place in it. According to physicist Kip Thorne, Einstein's general relativity is the most beautiful physical theory ever invented, and it's changed everything we thought we knew about reality itself. Tonight, we'll journey through the cosmic tapestry in 3 parts. First, exploring how Einstein shattered Newton's view of reality, then discovering how curved space-time creates what we experience as gravity, and finally examining the mind-bending implications for time, free will, and the nature of past and present. Imagine yourself lying on an immense, elastic sheet that extends beyond the horizon in every direction. This cosmic bedsheet is extraordinarily sensitive, responsive to every object that rests upon it. Feel how your body creates a gentle depression in this fabric, a subtle valley in an otherwise flat landscape. Now imagine larger bodies, massive spheres representing planets and stars, creating deeper depressions, more profound valleys in this cosmic tapestry. This living, responsive fabric is what physicists call space-time, the very foundation of our reality. This visualization helps us grasp one of the most revolutionary scientific insights ever conceived, that space and time are not separate, independent aspects of reality, but intimately interwoven dimensions of a single cosmic fabric. This understanding didn't come easily to human thought. For centuries, our conception of the universe was fundamentally different, shaped by intuitions that seemed unquestionable until a patent clerk in Switzerland dared to question them. Before Einstein's revolutionary work in the early 20th century, our understanding of the universe was largely Newtonian. Sir Isaac Newton, whose brilliant mind gave us calculus and the laws of motion, envisioned space as an absolute, fixed stage, an immutable grid upon which the drama of the cosmos played out. In this view, space was essentially a container, a three-dimensional void in which objects existed and moved. It was passive, unchanging, and completely separate from the objects within it. Similarly, Newton conceived of time as an absolute flow, a universal river moving at the same rate everywhere in the cosmos. 1 second on Earth was exactly the same as 1 second near a massive star or in the emptiest reaches of space. Time was seen as a fundamental constant, ticking away uniformly and independently of all events and objects in the universe. This view aligned perfectly with our intuitive experience. After all, doesn't time seem to flow at the same rate regardless of where we are? Einstein's genius lay in recognizing that this intuitive picture, however natural it seemed, was fundamentally incorrect. In his theory of special relativity, published in 1905, he proposed that space and time were not separate entities, but aspects of a unified four-dimensional continuum he called space-time. More shocking still, he demonstrated that the flow of time was not absolute but relative, depending on the observer's state of motion. 10 years later, with his general theory of relativity, Einstein completed this reconceptualization by showing that this space-time fabric is not flat and rigid but dynamic and responsive. It curves in the presence of matter and energy. This curvature is what we experience as gravity. In Einstein's framework, the Earth doesn't orbit the Sun because of a mysterious force acting across empty space, as Newton had proposed. Rather, the massive Sun creates a deep depression in the space-time fabric, and the Earth rolls around this cosmic valley like a marble circling a funnel. To help visualize this concept, physicists often use the analogy of a trampoline with a bowling ball placed in the center. The ball creates a depression, causing the trampoline's surface to curve. If you then roll a marble across the trampoline, it will naturally follow a curved path around the bowling ball, not because the ball is exerting a mysterious, pulling force on the marble, but because the marble is following the curvature of the surface itself. This is analogous to how planets orbit stars. They're following the natural contours of curved spacetime. What makes this concept so profound is that it completely transforms our understanding of gravity. In Newton's view, gravity was a force that somehow acted instantaneously across empty space. a concept that even Newton himself found somewhat mysterious. How could one object instantaneously know about and respond to another object across vast distances? Einstein's insight was that gravity isn't a force at all in the conventional sense, but a manifestation of the geometry of space-time. Objects move the way they do because they're following the path of least resistance through curved space-time, what physicists call a geodesic. This reconceptualization of reality challenges our intuitive understanding of the universe in profound ways. Perhaps most significantly, it reveals that space and time are not fixed and absolute, but relative and interconnected. One of the most counterintuitive implications is that time flows differently depending on gravity and velocity. Consider two identical clocks, one placed at sea level and another atop a mountain. The clock at sea level, being closer to Earth's mass, experiences slightly more space-time curvature, and as a result, it actually ticks more slowly than the clock on the mountain. This effect, called gravitational time dilation, has been measured with extremely precise atomic clocks, confirming Einstein's predictions. Though the difference is tiny in Earth's relatively weak gravitational field, just microseconds over a human lifetime, it becomes dramatically significant near massive objects like neutron stars or black holes. Similarly, time dilation occurs with velocity. If you were to travel in a spaceship at a significant fraction of the speed of light, time would pass more slowly for you than for those you left behind on Earth. This isn't just a perceptual illusion. It's a real physical effect that has been confirmed countless times in particle accelerators, where fast-moving particles decay more slowly than identical particles at rest. These effects sound like science fiction, but they're essential considerations in technologies we use every day. The Global Positioning System, GPS, satellites orbiting Earth move at high speeds and experience less gravity than we do on the surface. Both factors cause their clocks to tick at a different rate than Earth-based clocks. If engineers didn't account for these relativistic effects by programming the satellites to adjust their time calculations, GPS would accumulate errors of about 10 kilometers per day, rendering the system useless for navigation. Perhaps the most profound implication of Einstein's space-time concept is what it suggests about the nature of past, present, and future. In our everyday experience, we perceive time as flowing, with a clear distinction between past events, fixed and unchangeable, present events, being experienced now, and future events, undetermined and yet to happen. But in the four-dimensional space-time framework, this distinction becomes less clear. Mathematically, Einstein's equations treat time as simply another dimension, different from, but fundamentally similar to the three spatial dimensions. This has led some physicists to propose what's called the block universe view, in which past, present, and future all exist simultaneously in the four-dimensional tapestry of space-time. In this view, our perception of a flowing, present moment moving from past to future is something of an illusion, a result of how our consciousness interfaces with the four-dimensional reality. The physicist Hermann Minkowski, who helped formalize the mathematics of space-time, expressed this view eloquently. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. In this perspective, the universe is not a three-dimensional space evolving through time, but a static four-dimensional structure that already contains all of history, past, present, and future. This view raises profound philosophical questions about determinism and free will. If the future already exists in some sense within the four-dimensional tapestry, does that mean our future actions are predetermined? Or is there still room for choice and contingency within this framework? Physicists and philosophers continue to debate these questions with no clear consensus. What's particularly fascinating about Einstein's space-time concept is how it reconciles seemingly contradictory observations. For instance, in special relativity, Einstein showed that observers moving at different velocities will disagree about whether two distant events happen simultaneously. This seems to create a paradox. How can one observer correctly claim that event A happened before event B, while another equally correct observer claims they happened in the opposite order? The resolution lies in understanding that in the four-dimensional space-time framework, there's no universal now that spans the entire universe. Different observers moving relative to each other effectively slice through the four-dimensional tapestry at different angles, experiencing different three-dimensional snapshots of the whole. Neither observer is wrong. They're simply experiencing different perspectives on the same four-dimensional reality. As you continue to relax and drift closer to sleep, take a moment to appreciate how profoundly this view transforms our understanding of the cosmos. The universe is not a collection of objects in empty space, with time flowing independently in the background. Instead, it's an intricate, interconnected fabric where space, time, matter, and energy are all aspects of a single cosmic tapestry. Your body, the Earth, distant stars, and even the light from those stars are all patterns woven into this grand cosmic fabric. This perspective gives us a new appreciation for our place in the cosmos. We are not merely objects moving through space and time. We are embedded within the very fabric of reality, connected to all other parts of the universe through the intricate weave of space-time. The gravity that keeps your body on your bed right now is not a force pulling you down, but the gentle curvature of space-time created by the Earth's mass. The starlight that traveled billions of years to reach us followed paths determined by the varying curves and contours of this cosmic tapestry. As Einstein's theories have been tested with increasing precision over the past century, they have passed every experimental challenge. From the bending of starlight around the sun during a solar eclipse, first observed in 1919, to the precise measurements of gravitational waves, first detected in 2015, the evidence consistently confirms that space-time is indeed a dynamic, responsive fabric that forms the foundation of our reality. Yet Einstein's theories, revolutionary as they are, may not be the final word on the nature of space-time. At extremely small scales, the quantum realm, or in conditions of extreme gravity, such as the center of a black hole or the first moments of the Big Bang, Einstein's equations break down. In these domains, we need a theory of quantum gravity that can reconcile general relativity with quantum mechanics. Various approaches, from string theory to loop quantum gravity, are attempting to provide this unified description, potentially revealing space-time to have even more exotic properties at its most fundamental level. As you visualize this cosmic fabric stretching throughout the universe, let's examine more closely how this tapestry responds when massive objects move across it, creating ripples that travel outward like waves on a pond's surface. These ripples in space-time, known as gravitational waves, represent one of the most exciting frontiers in our exploration of the cosmic tapestry. As you visualize this cosmic fabric stretching throughout the universe, let's examine more closely how this tapestry responds when massive objects move across it, creating ripples that travel outward like waves on a pond's surface. Imagine standing at the edge of a perfectly still lake on a calm summer evening. You pick up a stone and toss it into the water. From the point of impact, concentric circles begin to spread outward, traveling across the surface until they reach the distant shore. These ripples carry energy from the stone's impact across the entire body of water, subtly affecting everything in their path. In a similar way, the fabric of space-time ripples when disturbed by the acceleration of massive objects. These disturbances, known as gravitational waves, propagate through the universe at the speed of light, carrying energy and information about the cosmic events that created them. Unlike the ripples on our lake, however, gravitational waves remained invisible to human detection for a century after their theoretical prediction, a testament to both their subtlety and the remarkable ingenuity required to finally observe them. Einstein first predicted the existence of gravitational waves in 1916, just a year after publishing his general theory of relativity. The mathematics of his theory suggested that accelerating masses would create these ripples in space-time, much as accelerating electrical charges create electromagnetic waves. Yet Einstein himself was ambivalent about whether these waves truly existed or were merely mathematical artifacts of his equations. He changed his mind several times on the subject, at one point publishing a paper claiming to prove they didn't exist, only to retract it when an error was pointed out. This uncertainty was understandable. The theory predicted that gravitational waves would be extraordinarily faint, so subtle that detecting them seemed beyond the reach of any conceivable technology. Even the most violent cosmic events would produce waves that, by the time they reached Earth, would distort space by less than the width of an atomic nucleus. How could scientists possibly measure such infinitesimal changes? The challenge of detecting these elusive ripples in space-time remained insurmountable for decades. Yet theoretical physicists continued to study gravitational waves, growing increasingly convinced of their reality and importance. In the 1960s, physicist Joseph Weber built the first gravitational wave detectors, large aluminum cylinders that he hoped would vibrate in response to passing gravitational waves. Though Weber claimed detections, his results couldn't be replicated, and the scientific community concluded that his instruments lacked the necessary sensitivity. A more promising approach emerged with the concept of laser interferometry, using laser beams to measure minute changes in distance with extraordinary precision. This led to the development of the Laser Interferometer Gravitational Wave Observatory, LIGO, a project of unprecedented ambition and technical sophistication. LIGO consists of two identical detectors, one in Hanford, Washington, and the other in Livingston, Louisiana, separated by 3,000 kilometers. Each detector features two perpendicular arms, each 4 kilometers long, forming an L shape. The operating principle of these remarkable instruments is both elegant and ingenious. A laser beam is split and sent down each arm, bouncing back and forth between mirrors at the ends before recombining. When the beams recombine, they're precisely calibrated to create a pattern of interference. If a gravitational wave passes through the detector, it will stretch space-time in one direction while compressing it in the perpendicular direction, slightly changing the relative lengths of the two arms. This minute change alters the interference pattern, creating a measurable signal. The sensitivity required to detect gravitational waves is almost beyond comprehension. LIGO can measure changes in the 4-kilometer arm lengths of less than 1/10,000th the width of a proton, equivalent to measuring the distance to the nearest star with an accuracy smaller than the width of a human hair. Achieving this sensitivity required overcoming countless technical challenges, from isolating the instruments from seismic vibrations to accounting for the quantum nature of light itself. After decades of development and an initial observational run that detected nothing, LIGO underwent a major upgrade to increase its sensitivity. The enhanced, advanced LIGO began operations in September 2015, just days after the upgraded detectors were activated. Before the official observing run had even begun, they recorded a signal that would change astronomy forever. On September 14, 2015, both LIGO detectors captured the distinctive signal of gravitational waves washing over Earth. The signal lasted less than a quarter of a second, but its form told an extraordinary story. The frequency and amplitude of the waves matched precisely what would be expected from the final moments of two black holes spiraling into each other and merging. The signal revealed that about 1.3 billion years ago, two black holes, one 29 times the mass of our Sun, the other 36 times, completed their cosmic dance by colliding and forming a single black hole of 62 solar masses. The missing 3 solar masses, an amount of matter equivalent to 3 of our suns, was converted into pure energy in the form of gravitational waves, following Einstein's famous equation E equals mc squared. In that brief moment, the merger released more energy than all the stars in the observable universe combined. Yet by the time these powerful waves reached Earth, they had spread out so much that they changed the length of LIGO's 4-kilometer arms by just 1,000th the diameter of a proton. This detection, announced to the world in February 2016, represented a landmark achievement in human inquiry, the culmination of a century-long quest to confirm a key prediction of Einstein's theory and the birth of an entirely new way of observing the cosmos. The 2017 Nobel Prize in Physics was awarded to Rainer Weiss, Kip Thorne, and Barry Barish for their decisive contributions to the LIGO detector and the observation of gravitational waves. Since that first historic detection, LIGO and its European counterpart Virgo have observed dozens more gravitational wave events, most from binary black hole mergers, but also including the spectacular collision of 2 neutron stars. This latter event, detected in August 2017, was particularly significant because it was also observed across the electromagnetic spectrum by conventional telescopes, the first multi-messenger observation including gravitational waves. To understand how gravitational waves are created, we need to consider what happens when massive objects accelerate. Any mass curves the space-time around it, creating the effect we experience as gravity. When that mass accelerates, changing its speed or direction, the curvature must change accordingly. This change cannot happen instantaneously throughout space, but must propagate outward at the speed of light, creating ripples in the fabric of space-time. The most powerful sources of gravitational waves are systems where extremely massive objects undergo extreme acceleration. Binary systems of black holes or neutron stars provide ideal conditions. As these dense objects orbit each other, they lose energy through gravitational radiation, causing them to spiral closer together. As they get closer, they orbit faster, generating stronger gravitational waves. This creates a characteristic chirp pattern in the signal, increasing in both frequency and amplitude, culminating in a final merger where the gravitational wave emission peaks before rapidly fading away. What makes gravitational waves so remarkable is the nature of their interaction with matter. Unlike electromagnetic waves, which can be absorbed, reflected, or scattered by the matter they encounter, gravitational waves pass through almost everything with minimal interaction. This transparency allows them to carry information across vast cosmic distances virtually unchanged, providing a pristine record of the events that created them. This property opens an entirely new window onto the universe. Traditional astronomy has been limited primarily to observing electromagnetic radiation, light in its various forms, from radio waves to gamma rays. But many of the most energetic and interesting cosmic phenomena are obscured by dust or gas, or emit no electromagnetic radiation at all. Gravitational waves allow us to hear these previously invisible events, complementing our ability to see with traditional telescopes. The analogy to hearing is particularly pertinent. The frequencies of gravitational waves detected by LIGO fall within the human audible range, allowing scientists to convert the signals directly into sound. The first detection produced a distinctive chirp, a rising tone lasting a fraction of a second. This auditory representation has led astronomers to speak of listening to the universe, adding a new sensory dimension to our cosmic observations. The implications of gravitational wave astronomy extend far beyond confirming Einstein's century-old prediction. This new observational tool promises to reveal aspects of the universe that have remained hidden throughout human history. Binary black hole mergers, now routinely detected, provide insights into the population and properties of these mysterious objects. The neutron-star collision observed in 2017 confirmed theories about the origin of heavy elements like gold and platinum, which are forged in such energetic events. Looking forward, gravitational wave astronomy may help solve numerous cosmic mysteries. It could reveal the nature of dark matter, the invisible substance that appears to make up about 85% of the universe's mass. It might provide insights into the early universe, potentially detecting echoes of the Big Bang itself through primordial gravitational waves. It could even test alternative theories of gravity that diverge from Einstein's predictions in extreme conditions. The field continues to advance rapidly. LIGO and Virgo undergo regular upgrades to increase their sensitivity, allowing detection of ever more distant and diverse sources. New detectors are under construction or planning, including KAGRA in Japan and LIGO India. Perhaps most ambitious is the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory planned by the European Space Agency for the 2030s. With arms millions of kilometers long, LISA will detect lower-frequency gravitational waves from sources like supermassive black hole mergers and binary white dwarf stars. As our ability to detect gravitational waves improves, we can expect to build an increasingly detailed soundscape of the universe, a record of cosmic collisions, explosions, and perhaps entirely unexpected phenomena that have remained invisible to traditional astronomy. Just as the invention of the telescope revolutionized our understanding of the cosmos 4 centuries ago, gravitational wave detectors are opening up vast new territories for exploration. What makes this scientific achievement particularly profound is its connection to the fundamental nature of reality. Gravitational waves are not merely another type of radiation traveling through space. They are ripples in the fabric of space-time itself. Their detection provides direct confirmation that space-time is a dynamic entity, responsive to the matter and energy within it. Each observation of gravitational waves reinforces Einstein's revolutionary conception of gravity not as a force acting through space, but as the geometry of space-time itself. As you continue to relax and drift towards sleep, imagine these cosmic ripples passing through you at this very moment. Gravitational waves from distant black hole mergers, neutron-star collisions, and perhaps phenomena we haven't yet discovered are continually washing over Earth, subtly stretching and compressing the space you occupy. Though far too weak to feel, these ripples connect you directly to some of the most energetic events in the cosmos, a tangible link between your quiet moment of repose and the dynamic, ever-changing tapestry of the universe. While gravitational waves represent temporary ripples in the cosmic fabric, let's now explore regions where space-time is permanently and extremely curved. The mysterious objects we call black holes, where the fabric of reality is stretched to its very limits. As we contemplate these cosmic abysses where space-time curves to its breaking point, let's shift our perspective to consider how the fabric of the universe is not static but expanding, stretching like an inflating balloon carrying galaxies along with it. This cosmic expansion represents one of the most profound discoveries in the history of science, fundamentally transforming our understanding of the universe and our place within it. For most of human history, the universe was imagined as eternal and unchanging in its overall structure. Even Einstein, when formulating his general theory of relativity in 1915, assumed the universe must be static, neither expanding nor contracting. His equations suggested otherwise, indicating that the universe should be dynamically changing. But he considered this so implausible that he introduced a cosmological constant into his equations specifically to counteract gravity and maintain a static universe. He would later call this his greatest blunder. The paradigm shift began in the 1920s with the work of an American astronomer named Edwin Hubble. Using the newly built 100-inch Hooker telescope at Mount Wilson Observatory, then the largest telescope in the world, Hubble made two revolutionary discoveries. First, he proved that the fuzzy nebulae observed in the night sky were actually distant galaxies, immense collections of stars far beyond our own Milky Way. This dramatically expanded the known size of the universe. His second discovery was even more profound. By analyzing the light from these distant galaxies, Hubble noticed something peculiar. Their spectral lines were shifted toward the red end of the spectrum. This redshift indicated that these galaxies were moving away from us, an effect similar to how the sound of a receding train's whistle drops in pitch. Moreover, Hubble found a pattern. The farther away a galaxy was, the faster it appeared to be receding. This relationship, now known as Hubble's law, provided the first observational evidence that the universe is expanding. To understand this expansion, imagine a balloon with dots drawn on its surface. As you inflate the balloon, every dot moves away from every other dot. From the perspective of any single dot, all other dots appear to be moving away, with the most distant dots receding the fastest. Importantly, the dots themselves aren't moving across the surface of the balloon. They remain fixed on the rubber. Rather, it's the rubber itself, the space between the dots, that's stretching. This analogy captures the essence of cosmic expansion. Galaxies aren't racing away from each other through space like shrapnel from an explosion. Instead, space itself is stretching, carrying galaxies along with it. This distinction is crucial for understanding the true nature of cosmic expansion. It's not a movement through space, but a stretching of space itself. This expanding universe naturally suggests a beginning, a time when everything was much closer together, hotter, and denser. Following this logic backward led to the development of the Big Bang Theory, first proposed by Georges Lemaitre, a Belgian priest and physicist in the 1920s. The theory suggests that the universe began from an incredibly hot, dense state about 13.8 billion years ago and has been expanding and cooling ever since. The most compelling evidence for the Big Bang came in 1964, when astronomers Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, CMB, a faint glow permeating all of space. This radiation represents the afterglow of the Big Bang, the oldest light in the universe. When the universe was about 380,000 years old, it cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. This allowed photons, particles of light, to travel freely through space for the first time. These photons have been traveling through the expanding universe ever since, their wavelengths stretched by cosmic expansion until they now appear as microwave radiation. The discovery of the CMB provided strong confirmation of the Big Bang theory and earned Penzias and Wilson the Nobel Prize in Physics. Subsequent satellite missions like COBE, WMAP, and Planck have mapped this radiation in extraordinary detail, revealing tiny temperature fluctuations that correspond to the seeds of cosmic structure, the earliest precursors of the galaxies and galaxy clusters we see today. The expansion of the universe was long assumed to be slowing down due to the mutual gravitational attraction of all matter. Just as a ball thrown upward slows due to Earth's gravity, the expansion of the universe should decelerate under the influence of its own gravity. But in the late 1990s, two independent teams of astronomers made a shocking discovery that would once again revolutionize our understanding of the cosmos. These teams were studying Type I supernovae, exploding stars that serve as standard candles because they always reach approximately the same peak brightness. By measuring how bright these supernovae appear from Earth, astronomers can determine their distance. When combined with measurements of their redshift, this allows for a precise tracking of the universe's expansion rate over time. To everyone's surprise, the data showed that the expansion of the universe isn't slowing down, it's speeding up. The universe's expansion is accelerating, as if some mysterious repulsive force is overcoming gravity on the largest scales. This force, dubbed dark energy, appears to be intrinsic to the fabric of space itself. The more space expands, the more dark energy there is, creating a self-reinforcing cycle of ever faster expansion. This discovery, which earned the 2011 Nobel Prize in Physics, resurrected Einstein's cosmological constant in a new form. What Einstein had introduced as a mathematical fix to maintain a static universe might actually represent a fundamental property of space, an energy density inherent to the vacuum itself. Alternative explanations include a dynamic energy field called quintessence or modifications to Einstein's theory of gravity at cosmic scales. Whatever its nature, dark energy constitutes about 68% of the total energy content of the universe, making it the dominant component of our cosmos. The accelerating expansion of the universe has profound implications for its future. As space continues to stretch at an ever-increasing rate, galaxies beyond a certain distance, called the cosmic event horizon, are receding faster than the speed of light. This doesn't violate Einstein's special relativity because the galaxies aren't moving through space faster than light. Rather, the space between us and them is expanding so rapidly that light emitted from these galaxies will never reach us, no matter how long we wait. This cosmic event horizon is currently estimated to be about 16 billion light-years away. Galaxies beyond this distance are forever inaccessible to us. We will never be able to observe them or communicate with them. More troublingly, galaxies that are currently visible will eventually cross this horizon as the expansion accelerates, gradually disappearing from our observable universe. In the far future, observers in the Milky Way, or whatever galaxy our descendants might inhabit, will see an increasingly empty cosmos, with all other galaxies having receded beyond the horizon of visibility. If dark energy maintains its current properties, the universe faces a bleak future often called the heat death or big freeze. As galaxies become increasingly isolated, stars will burn out, black holes will evaporate through Hawking radiation, and matter itself may eventually decay. The universe will approach a state of maximum entropy, a cold, dark, nearly featureless void where no structured complexity or life as we know it could exist. An even more dramatic scenario, called the Big Rip, could occur if dark energy strengthens over time. In this case, the accelerating expansion would eventually become so powerful that it would tear apart galaxies, solar systems, planets, and ultimately atoms themselves. Everything would be ripped asunder by the relentless stretching of space. Alternative scenarios depend on the true nature of dark energy. If it weakens over time, gravity might eventually reassert dominance, slowing and reversing the expansion. This could lead to a big crunch, where the universe collapses back on itself, potentially followed by a new Big Bang in an oscillating universe model. However, current observations suggest this scenario is unlikely. Another possibility is a big bounce, where quantum effects prevent a true singularity at the big crunch, causing the universe to rebound into a new expansion phase. Some theories also propose a big freeze, followed by a spontaneous quantum fluctuation that generates a new Big Bang, creating a form of cosmic renewal. These various possible fates of the universe raise profound philosophical questions. The apparent beginning of the universe in the Big Bang challenges us to consider what, if anything, came before, and whether such a question even makes sense when time itself may have begun with the Big Bang. Similarly, the prospect of an eventual heat death or big rip confronts us with the possibility of a universe that, while perhaps infinite in duration, might contain only a finite window in which complex structures like galaxies, stars, planets, and life can exist. These questions touch on ancient philosophical and theological debates about creation, purpose, and finitude. Is a universe with a beginning necessarily created? Does an ending imply purpose or meaninglessness? How do we reconcile the apparent finite duration of cosmic habitability with human aspirations for permanence or transcendence? The expanding universe also raises questions about cosmic uniqueness. If our observable universe had a beginning in the Big Bang, might there be other bubble universes with their own Big Bangs, collectively forming a vast multiverse? Some inflationary models of the early universe suggest that the rapid expansion immediately after the Big Bang could have generated multiple bubble universes, each with potentially different physical laws and constants. The cosmic expansion has practical implications for astronomy as well. As the universe continues to expand, the evidence that led to our current understanding, the redshift of distant galaxies, the cosmic microwave background, will gradually become harder to detect. In the far future, astronomers might be unable to discover that the universe is expanding or had a hot, dense beginning. This raises the intriguing possibility that there might be aspects of cosmic structure and history that are similarly undetectable to us now, limiting our ability to fully understand our cosmic context. Despite these profound implications and remaining mysteries, the discovery of cosmic expansion stands as one of humanity's greatest intellectual achievements. In just a century, we've progressed from believing the universe consists solely of the Milky Way and a static cosmos to understanding that we inhabit one galaxy among billions in an expanding universe that began in a hot, dense state and is accelerating toward an open future. This expanding cosmic tapestry provides the largest scale context for all other phenomena we observe. The gravitational waves we discussed earlier propagate through this expanding medium. The black holes with their extreme curvature exist within this globally expanding framework. Every structure in the cosmos, from superclusters of galaxies down to planets and life itself, has formed against the backdrop of this cosmic expansion. As you continue to relax and contemplate these vast cosmic processes, consider that the space around you is not static but slowly stretching. The atoms in your body were forged in stars that formed within this expanding framework. The light reaching your eyes from distant sources has traveled through expanding space, its wavelength stretched by the cosmic expansion. You exist within this dynamic cosmic tapestry, connected to its past and future through the fundamental properties of space-time itself. While the universe expands on the largest scales, let's now examine how the fabric of space-time behaves at the smallest scales, where quantum effects create a foamy, fluctuating structure that challenges our very conception of space and time. While the universe expands on the largest scales, let's now examine how the fabric of space-time behaves at the smallest scales, where quantum effects create a foamy, fluctuating structure that challenges our very conception of space and time. Imagine standing on a beach, gazing out at the ocean on a calm day. From your vantage point, the water's surface appears smooth and continuous, a gently undulating plane extending to the horizon. But if you were to look at that same surface through a powerful microscope, you would discover a very different reality. a turbulent world of tiny ripples, bubbles, and spray, constantly forming and dissolving in a chaotic dance. This contrast between apparent smoothness at large scales and frenetic activity at small scales provides a fitting analogy for how physicists now understand the fundamental nature of space-time. The smooth four-dimensional continuum described by Einstein's general relativity, the cosmic tapestry we've been exploring, may be just a large-scale approximation of a much more complex and dynamic reality that emerges at the smallest possible scales. This concept, known as quantum foam or space-time foam, was first proposed by the physicist John Wheeler in 1955. Wheeler, who also coined the term black hole, was exploring the profound implications of applying quantum mechanics to the fabric of space-time itself. His insights suggested that at incredibly tiny scales, specifically at the Planck length of approximately 10 to the power of -35 meters, space-time would no longer appear smooth, but would instead seethe with quantum fluctuations, appearing foamy or frothy in nature. To appreciate the scale we're discussing, consider that the Planck length is to the size of an atom what an atom is to the size of the entire observable universe. It is unimaginably small, far beyond our current experimental reach and perhaps beyond any possible direct observation. Yet theoretical considerations suggest that at this scale, the fundamental nature of reality undergoes a dramatic transformation. The concept of quantum foam emerges from the intersection of two revolutionary theories of 20th century physics: general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time caused by mass and energy. Quantum mechanics, on the other hand, reveals that at subatomic scales, physical properties like position and momentum are inherently uncertain and particles exhibit wave-like behavior. One of the most remarkable predictions of quantum mechanics is the uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that certain pairs of physical properties, such as position and momentum, or energy and time, cannot be simultaneously measured with arbitrary precision. The more precisely you measure one property, the less precisely you can know the other. When applied to the vacuum of space, this uncertainty principle leads to a startling conclusion. Empty space isn't truly empty. Instead, the vacuum seethes with virtual particles, pairs of particles and antiparticles that spontaneously pop into existence and then annihilate each other almost immediately. These particle-antiparticle pairs borrow energy from the vacuum for their brief existence, in accordance with the energy-time uncertainty principle, which allows energy conservation to be temporarily violated over very short time scales. These quantum fluctuations in the vacuum have been experimentally verified through effects like the Casimir force, a small attractive force between two parallel uncharged conducting plates in a vacuum, caused by quantum fluctuations. The existence of Hawking radiation from black holes, which we discussed earlier, also relies on these vacuum fluctuations. When we extend quantum principles to space-time itself, we encounter quantum foam. Just as the energy of the vacuum fluctuates, creating virtual particles, the geometry of space-time should also fluctuate at the Planck scale. The shorter the distance and time scales we examine, the larger these fluctuations become. At the Planck scale, these fluctuations in the fabric of reality become so violent and significant that our conventional notions of space and time break down entirely. Imagine space-time at this scale as a roiling sea of microscopic black holes, wormholes, and other exotic topological structures, constantly forming, merging, dividing, and dissolving. These structures might exist for only the briefest moments, around 10 to the power of -43 seconds, the Planck time, but they would fundamentally alter the nature of reality at this scale. Space might no longer be continuous but composed of discrete units. Time might lose its directional flow, becoming granular or perhaps even meaningless as a separate dimension. In this quantum foam, the distinction between something and nothing blurs. The vacuum becomes a dynamic entity, pregnant with potential, where particles, energy, and even the fabric of space-time itself emerge from and dissolve back into a fundamental quantum reality. The seemingly empty void is revealed as a teeming ocean of possibility. While direct observation of quantum foam remains beyond our current technological capabilities, scientists have proposed various experiments to detect its effects indirectly. One approach involves observing light from distant cosmic sources. If space-time is foamy rather than smooth, photons traveling across vast cosmic distances might experience slight delays or distortions that could, in principle, be measured. Several experiments have placed upper limits on the scale of quantum foam, but definitive evidence remains elusive. The concept of quantum foam has profound implications for our understanding of reality. Perhaps most significantly, it suggests that space and time themselves may not be fundamental aspects of reality, but emergent properties. Large-scale approximations that arise from more basic quantum processes, much as the apparent smoothness of water emerges from the collective behavior of countless water molecules. This perspective represents a radical departure from our intuitive understanding of reality. We naturally think of space as the stage upon which physical processes unfold, and time as the universal flow that orders events. But quantum foam suggests that space and time might be more like temperature or pressure, macroscopic properties that emerge from the collective behavior of microscopic constituents rather than fundamental features of reality. If space and time are emergent rather than fundamental, what lies beneath them? What is the true bedrock of reality from which our familiar four-dimensional space-time emerges? This question drives much of contemporary theoretical physics, particularly approaches that seek to reconcile quantum mechanics with general relativity, a challenge that has resisted solution for nearly a century. General relativity beautifully describes gravity and the large-scale structure of the universe, but breaks down its singularities like the center of black holes or the beginning of the Big Bang. Quantum mechanics brilliantly accounts for the behavior of matter and energy at subatomic scales, but struggles to incorporate gravity into its framework. The search for a theory of quantum gravity, a unified description that works across all scales, represents one of the greatest outstanding challenges in theoretical physics. Several candidate approaches to quantum gravity incorporate the concept of quantum foam in different ways. String theory, perhaps the most widely studied approach, suggests that the fundamental constituents of reality are not point-like particles, but tiny one-dimensional strings that vibrate in different patterns to create the particles we observe. In string theory, these strings exist in a higher dimensional space, and their vibrations give rise to particles, forces, and space-time itself. The quantum foam emerges from the complex interactions of these strings at the Planck scale. Another approach, loop quantum gravity, takes a more direct route to quantizing space-time itself. In this theory, space is not infinitely divisible, but composed of discrete units called spin networks or spin foams, essentially quantum atoms of volume. Time emerges from the evolution of these networks. At the Planck scale, space-time in loop quantum gravity would appear as a constantly changing network of interconnected loops, a literal realization of Wheeler's quantum foam. Other approaches include causal set theory, which models space-time as a discrete set of points connected by causal relationships, and asymptotic safety, which suggests that gravity might naturally become less strong at very high energies, avoiding the infinities that plague attempts to quantize gravity using conventional methods. Each of these approaches offers a different perspective on the fundamental nature of quantum foam and the structure from which space-time emerges. While they differ in their details, they share the revolutionary suggestion that space and time are not the fundamental arena of physics, but consequences of deeper quantum processes. This reconceptualization of space and time has philosophical implications that extend far beyond physics. If space and time are emergent rather than fundamental, what does this mean for our understanding of causality, determinism, and free will? If the underlying reality is fundamentally quantum and probabilistic, does this lend support to philosophical perspectives that emphasize indeterminism or multiple possibilities? The concept of quantum foam also raises questions about the nature of physical law itself. If space-time emerges from a more fundamental reality, might the laws of physics also be emergent rather than absolute? Could different regions of the universe, or different universes in a multiverse, have different emergent laws arising from the same underlying quantum reality? Some theoretical physicists have even suggested that consciousness itself might be connected to quantum processes in the brain that interact with the quantum nature of space-time. While such speculations remain highly controversial and far from mainstream scientific consensus, they illustrate how profoundly the concept of quantum foam challenges our conventional understanding of reality. The foamy nature of space-time at quantum scales also has practical implications for our understanding of the early universe. In the first moments after the Big Bang, the entire observable universe was compressed to a size where quantum gravitational effects would have dominated. Understanding quantum foam may be essential to developing a complete theory of cosmic origins and evolution. Similarly, the final stages of black hole evaporation through Hawking radiation would involve scales where quantum gravitational effects become significant. The resolution of the black hole information paradox, which we discussed earlier, likely requires a deeper understanding of how information is encoded in the quantum structure of spacetime itself. Perhaps most intriguingly, quantum foam might provide a natural mechanism for the emergence of spacetime itself. Some theoretical models suggest that our four-dimensional spacetime could have condensed or crystallized from a more chaotic quantum foam state in the early universe, much as a liquid crystallizes into a solid with a regular structure. In this view, the Big Bang might represent not the beginning of everything, but a phased transition in a pre-existing quantum reality, a transformation from a state where space and time had not yet emerged to the familiar four-dimensional continuum we now inhabit. As you continue to relax and contemplate these profound concepts, consider that the apparently solid matter of your body, the chair or bed supporting you, and the room around you all ultimately dissolve into quantum uncertainty at the smallest scales. The seemingly continuous space between atoms is actually a seething quantum foam, where virtual particles flicker in and out of existence, and the fabric of reality itself fluctuates in a constant quantum dance. This perspective offers a kind of cosmic humility. The reality we perceive and the concepts we use to understand it, including space and time themselves, may be approximations, emergent patterns arising from a deeper quantum reality that defies our intuitive understanding. Our most fundamental theories are not final answers, but steps on a continuing journey of discovery, as we attempt to peer ever deeper into the quantum heart of reality. As we contemplate the foamy nature of space-time at its smallest scales, let's consider how the fabric of reality might be folded or connected in ways that create shortcuts across the cosmos. The theoretical structures called wormholes, where the quantum foam might create tunnels through the cosmic tapestry. Imagine for a moment that you are holding a piece of paper. This paper represents the fabric of space-time, the very foundation of our universe. Now, fold that paper in half, bringing two distant points closer together. After the fold, take a pencil and punch a hole through both layers of the paper. This creates a shortcut between the 2 points, allowing you to traverse what was once a long distance in an instant. This simple act of folding and puncturing the paper serves as an apt analogy for what physicists theorize to be wormholes, hypothetical tunnels through the fabric of space-time that could connect distant regions of the universe or even different universes entirely. Wormholes emerged from the rich tapestry of solutions to Einstein's equations of general relativity. These equations fundamentally changed our understanding of gravity, space, and time, revealing that massive objects curve the space-time around them. Among the many solutions to these equations, some describe these extraordinary structures that could act as bridges between otherwise disconnected parts of the universe. While wormholes are a staple of science fiction, they are more than mere fantasy. They represent fascinating possibilities embedded within the framework of modern physics. The term wormhole was first coined by physicist John Archibald Wheeler in the 1950s, but the concept has roots in Einstein's theories. One of the most famous types of wormhole is the Einstein-Rosen bridge, which connects two black holes in a way that illustrates the profound implications of general relativity. However, the theoretical existence of these structures raises many questions about their stability and practicality for travel. To understand how wormholes might function, we must delve into the nature of space-time itself. In Einstein's general relativity, space and time are not fixed backgrounds, but dynamic entities that can be warped and manipulated. A wormhole theoretically connects two regions of space-time through a tunnel, allowing for travel that bypasses the normal paths through space. This means that instead of moving through the intervening distance, one could enter a wormhole and emerge instantaneously at a distant location. However, not all wormholes are created equal. Theoretically, there are two types of wormholes: traversable and non-traversable. Non-traversable wormholes are often considered theoretical constructs that connect two black holes but are not stable enough to allow for travel. If you were to attempt to cross such a wormhole, you would be crushed by the extreme gravitational forces present at the event horizons of the black holes. Traversable wormholes, on the other hand, would theoretically allow for safe passage between their two ends. For a wormhole to remain stable enough to permit travel, it would require what physicists call exotic matter, a form of matter with negative energy density. This exotic matter would counteract the gravitational forces that would otherwise cause the wormhole to collapse. However, the existence of exotic matter remains hypothetical at this point, and no evidence has yet been found to support its reality. One of the most intriguing aspects of wormholes is their potential to allow faster-than-light travel without violating the principles of special relativity. Since the wormhole itself connects 2 points in space-time rather than moving faster than light through space, it circumvents the cosmic speed limit established by Einstein. This opens up tantalizing possibilities for interstellar travel, enabling humanity to explore distant galaxies or even parallel universes in a manner that traditional space travel could never achieve. But the implications of traversable wormholes don't stop at mere travel. They also raise profound questions about time itself. If one were to travel through a wormhole connecting different points in space-time, it might be possible to manipulate time, effectively allowing for time travel. Imagine stepping into a wormhole and emerging not just in a different location, but in a different era, potentially witnessing historical events or exploring the distant future. However, this raises complex paradoxes and ethical considerations. If time travel were possible, how would that affect the course of history? Would it be possible to alter past events, creating a ripple effect that changes the present? The grandfather paradox is a classic thought experiment that illustrates these dilemmas. If someone travels back in time and prevents their grandparents from meeting, how could they ever have been born to undertake that journey in the first place? Despite the tantalizing possibilities that wormholes present, most physicists remain skeptical about their actual existence in reality. Theoretical models suggest that traversable wormholes might be unstable due to quantum effects, making them collapse before any traveler could pass through. Additionally, the requirement for exotic matter presents a significant barrier. While certain quantum field theories allow for negative energy densities, it has yet to be demonstrated that such matter could exist or be harnessed. Moreover, the very nature of space-time as we understand it may impose fundamental limits on the feasibility of wormholes. Our current understanding of physics, governed by general relativity and quantum mechanics, has yet to provide a complete framework that reconciles the two theories. The search for a theory of quantum gravity, one that consistently describes the behavior of gravity at quantum scales, remains an active area of research, and it's possible that wormholes may only be one of many exotic constructs that arise from this deeper understanding. As we consider these aspects of wormholes, it's essential to recognize their role in the broader narrative of our quest for understanding the universe. The exploration of wormholes taps into humanity's timeless fascination with the unknown, our desire to transcend the limits of our current existence and explore realms that lie beyond our immediate reach. They symbolize a bridge to imagination and possibility, challenging us to consider what lies beyond the boundaries of our familiar reality. While wormholes represent theoretical tunnels through the cosmic fabric, let's now explore how the tapestry of space-time might be affected by the strange phenomenon of quantum entanglement, what Einstein famously referred to as spooky action at a distance. This mysterious connection between particles challenges our traditional notions of locality and the separateness of objects, hinting at a deeper, more interconnected reality that transcends our conventional understanding of the universe. While wormholes represent theoretical tunnels through the cosmic fabric, let's now explore how the tapestry of space-time might be affected by the strange phenomenon of quantum entanglement, what Einstein called spooky action at a distance. Imagine, if you will, a vast cosmic tapestry stretching across the universe. From a distance, it appears as a continuous fabric, but upon closer inspection, you notice intricate threads connecting seemingly separate regions. These invisible threads don't merely lie upon the tapestry. They are woven into its very structure, perhaps even creating the fabric itself. This metaphor helps us visualize one of the most profound insights emerging in theoretical physics: the possibility that quantum entanglement and space-time are intimately connected, perhaps even two perspectives on the same underlying reality. Quantum entanglement stands as one of the most counterintuitive phenomena in modern physics. When two particles become entangled, they form a single quantum system such that the properties of each particle cannot be described independently of the other, regardless of how far apart they may be separated. Measure the spin of one entangled electron, and you instantly know the spin of its partner, even if that partner is on the opposite side of the universe. This phenomenon so disturbed Einstein that he, along with colleagues Boris Podolsky and Nathan Rosen, proposed the famous EPR paradox in 1935, suggesting that quantum mechanics must be incomplete. Einstein could not accept what appeared to be information traveling instantaneously between entangled particles, faster than light, which would violate his special theory of relativity. He believed there must be hidden variables that predetermine the outcomes of measurements, making the apparent connection between distant particles merely an illusion. However, in 1964, physicist John Bell devised a theorem that allowed this question to be tested experimentally. Subsequent experiments, most definitively those conducted by a LAN aspect in the early 1980s, confirmed that entanglement is real. The quantum world truly does exhibit this spooky action at a distance that so troubled Einstein. No hidden variable theory compatible with locality, the principle that objects are only directly influenced by their immediate surroundings, could explain the observed correlations between entangled particles. To understand entanglement more concretely, consider a simple example involving two electrons. Electrons possess a quantum property called spin, which can be measured as either up or down along any chosen axis. When two electrons are entangled in a particular way, their spins are correlated such that if one is measured as up, the other must be down, and vice versa. The peculiar aspect is that before measurement, quantum mechanics tells us that each electron exists in a superposition of both spin states simultaneously. It's only when we measure one electron that both instantly assume definite, correlated states. Crucially, this correlation persists regardless of the distance between the particles. If we separate our entangled electrons by sending one to Earth and the other to Alpha Centauri, more than 4 light-years away, measuring the Earth-bound electron would still instantaneously correlate with the state of its distant partner. This doesn't mean information travels faster than light. We still need conventional communication channels to compare the results, but it does indicate a profound non-locality in the quantum realm that challenges our intuitive understanding of space and separation. For decades, entanglement was primarily viewed as a curious feature of quantum mechanics, fascinating but somewhat divorced from questions about the nature of space-time, which fell under the domain of general relativity. These two pillars of modern physics, quantum mechanics and general relativity, have long existed in an uneasy relationship, each supremely successful in its domain but seemingly incompatible at a fundamental level. Quantum mechanics governs the behavior of the very small, while general relativity describes gravity and the large-scale structure of the universe. Where they should overlap, in phenomena like black holes or the early universe, our theories break down. However, in recent years, a remarkable connection has emerged that may help bridge this divide. In 2013, physicists Juan Meldacena and Leonard Susskind proposed the ER equals EPR conjecture, suggesting a deep relationship between quantum entanglement, EPR, and Einstein-Rosen bridges, AR, which are a type of wormhole solution in general relativity. Their revolutionary proposal suggests that entangled particles might be connected by microscopic wormholes, creating a physical link through space-time that explains their correlated behavior. This conjecture emerged from work on the black hole information paradox and holographic principles in string theory, particularly the anti-de Sitter/conformal field theory, ADS/CFT correspondence. This correspondence suggests that gravitational physics in a region of space can be equivalent to a quantum field theory operating on the boundary of that region, like a hologram encoding three-dimensional information on a two-dimensional surface. Within this framework, researchers discovered that quantum entanglement between particles in the boundary theory corresponds to geometric connections in the bulk spacetime. In other words, entanglement in the quantum realm appears to translate directly into the curvature and connectivity of spacetime itself. This suggests something profound. Entanglement isn't just a phenomenon that occurs within spacetime. It may be fundamental to creating spacetime. Mark van Ramsdonk of the University of British Columbia has taken this idea further, proposing that spacetime itself might emerge from quantum entanglement. In thought experiments where entanglement between different regions is gradually reduced, the corresponding spacetime begins to tear apart and fragment. This suggests that the coherent fabric of spacetime that we experience may be woven together by a complex network of quantum entanglements connecting the fundamental constituents of reality. If this perspective is correct, space and distance as we know them would be emergent concepts, not fundamental aspects of reality, but consequences of patterns of quantum entanglement. 2 points in space might be close together not because they are separated by a small geometric distance, but because the quantum systems at those points are highly entangled. Conversely, distant regions of space would correspond to systems with minimal entanglement. This view represents a profound inversion of our usual thinking. Rather than imagining particles existing within a pre-existing spacetime framework, spacetime itself would emerge from the entanglement relationships between more fundamental quantum entities. The smooth, continuous spacetime described by Einstein's equations would be a macroscopic approximation of a deeper quantum reality, much as the apparently smooth flow of water emerges from the collective behavior of countless water molecules. The implications of this perspective are far-reaching. If entanglement creates spacetime, then the non-local correlations of quantum mechanics are not occurring despite spacetime separation, but are actually creating that separation. The spooky action at a distance that troubled Einstein would not be a violation of spacetime principles, but rather a manifestation of the underlying quantum relationships that constitute spacetime itself. This approach offers tantalizing possibilities for resolving the conflict between quantum mechanics and general relativity. If spacetime emerges from quantum entanglement, then general relativity, which describes the dynamics of spacetime, would naturally arise as an emergent description of the collective behavior of quantum systems. The incompatibility between our theories might not require reconciling fundamentally different frameworks, but rather recognizing that one emerges from the other at appropriate scales. The ER=EPR conjecture also sheds new light on black holes and the information paradox. If entangled particles that fall into different black holes remain connected by microscopic wormholes, this could provide a mechanism for preserving information despite Hawking radiation. The information isn't lost, but encoded in subtle quantum correlations maintained through these wormhole connections. Furthermore, this perspective suggests new ways of thinking about the quantum nature of gravity. If spacetime itself is woven from quantum entanglement, then gravity, which Einstein revealed to be the curvature of spacetime, would inherently be a quantum phenomenon. The challenge would not be to quantize gravity as an independent force, but to understand how gravitational effects emerge from the underlying quantum entanglement structure. These ideas have inspired various approaches to quantum gravity, including tensor network models that represent spacetime as emerging from patterns of quantum entanglement. These models use mathematical structures called tensor networks to describe how quantum information is organized, with the geometry of spacetime emerging from this organization. Remarkably, these models can reproduce features of curved spacetime, including the behavior of black holes, suggesting they capture something essential about the relationship between quantum information and geometry. The entanglement spacetime connection also resonates with holographic principles, which suggest that the information contained in a volume of space can be encoded on its boundary. The most concrete realization of this principle is the ADS/CFT correspondence mentioned earlier, but the underlying idea may be more general. Our three-dimensional reality might be encoded in a lower-dimensional quantum system, with space itself emerging from patterns of entanglement in this more fundamental description. If these speculative ideas prove correct, they would represent one of the most profound shifts in our understanding of physical reality since Einstein's theories of relativity. Space and time, the fundamental arena in which we perceive all events to occur, would not be primary aspects of reality, but emergent consequences of a deeper quantum reality. The apparently empty void between objects would be revealed as a complex web of quantum relationships, with distance itself a measure of entanglement rather than an independent property. This perspective invites us to reconsider philosophical questions about the nature of reality. If space emerges from entanglement, then separateness itself may be something of an illusion, not in a mystical sense, but in a precise physical sense. Objects that appear distant and unconnected in our macroscopic experience may be linked through the underlying quantum entanglement that creates the space between them. The discrete, localized objects of our everyday experience would be surface patterns on a deeply interconnected quantum reality. While these ideas remain speculative and at the frontier of theoretical physics, they have inspired new experimental approaches to testing the relationship between quantum information and space-time. Some researchers propose measuring entanglement in quantum systems that mimic aspects of curved space-time, while others seek signatures of space-time emergence in high-energy physics experiments or cosmological observations. As you continue to relax and contemplate these profound connections, imagine the space around you not as empty void, but as a rich tapestry of quantum relationships. The apparent distances between objects, between the atoms in your body, between you and the walls of your room, between Earth and distant stars, may all emerge from patterns of quantum entanglement that weave reality together. The smooth continuum of space-time that we navigate daily may be a macroscopic approximation of a more fundamental reality where entanglement, not location, is the primary relationship. In this view, we are not merely objects located within space-time. We are patterns of entanglement that contribute to creating space-time itself. Our bodies, like everything else in the universe, participate in the vast network of quantum relationships from which the fabric of reality emerges. We are not just in the cosmic tapestry, we are of it, our very existence interwoven with the threads that create space and time. As we contemplate these quantum connections weaving through the cosmic fabric, let's now consider how the tapestry of space-time behaves near the beginning of our universe, at the moment of the Big Bang, where our current understanding of physics reaches its limits, and where the quantum nature of space-time becomes not just a theoretical curiosity, but a necessary framework for understanding our cosmic origins. As we contemplate these quantum connections weaving through the cosmic fabric, let's now consider how the tapestry of space-time behaves near the beginning of our universe, at the moment of the Big Bang, where our current understanding of physics reaches its limits. When we think of the Big Bang, many of us imagine a tremendous explosion, like a cosmic firework erupting in pre-existing empty space. This intuitive picture, however, fundamentally misrepresents the nature of the event that gave birth to our universe. The Big Bang was not an explosion in space. It was the beginning of space itself, along with time and all the physical laws that govern our reality. To better grasp this concept, imagine watching a film of the expanding universe running backward. As we rewind through cosmic history, we see galaxies drawing closer together, the spaces between them shrinking. Stars and galaxies, once separated by billions of light years, begin to crowd together. The universe grows hotter and denser as all matter and energy converge. Continue this backward journey far enough, and eventually all the matter and energy in the observable universe compresses into an extraordinarily hot, dense state, smaller than an atom, and ultimately to what mathematically appears to be a single point. A singularity where density and temperature become infinite, and the very fabric of space-time curves to its breaking point. This mental exercise highlights a profound truth. When we talk about the Big Bang, we're describing not just the origin of matter and energy, but the beginning of space and time themselves. There was no outside into which the universe exploded, no before in which something triggered the event. The Big Bang represents the boundary of our physical reality, the edge of space-time itself. The standard Big Bang theory, developed primarily in the mid-20th century through the work of physicists like George Gamow, Ralph Alpher, and Robert Herman, describes our universe as emerging from this incredibly hot, dense state approximately 13.8 billion years ago. This theory rests on several key observational pillars: the expansion of the universe discovered by Edwin Hubble, the abundance of light elements, particularly hydrogen and helium, that matches predictions for nuclear synthesis in the early universe, and perhaps most importantly, the cosmic microwave background radiation, the afterglow of the Big Bang itself, first detected in 1964 by Arno Penzias and Robert Wilson. This cosmic microwave background, CMB, represents the oldest light in the universe, released when the universe had cooled enough for electrons to combine with protons to form neutral hydrogen atoms, allowing photons to travel freely for the first time. This occurred when the universe was about 380,000 years old, still in its infancy on cosmic timescales. The remarkable uniformity of this radiation, with temperature variations of only about 1 part in 100,000 across the entire sky, tells us that the early universe was extraordinarily homogeneous, yet contained the seeds of the cosmic structure we observe today. As we push our understanding back toward the beginning, we encounter increasingly extreme conditions. At about 1 second after the Big Bang, the universe was filled with a sea of protons, neutrons, electrons, photons, and neutrinos at temperatures of about 10 billion Kelvin. Going back further, to the first microseconds, quarks and gluons roamed freely before cooling enough to combine into protons and neutrons. And in the first fraction of a nanosecond, conditions were so extreme that even our current understanding of particle physics becomes inadequate to describe what occurred. At the very beginning, the Planck epoch, occurring within the first 10 to the power of -43 seconds, an unimaginably brief instant. All 4 fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single force. Space-time itself would have been subject to quantum fluctuations, with the distinction between space and time possibly becoming meaningless. Here, at the very edge of our understanding, general relativity and quantum mechanics both apply, yet fundamentally conflict with each other. We need a theory of quantum gravity, a framework that successfully merges these 2 pillars of modern physics, to fully describe these earliest moments. One of the most significant refinements to the original Big Bang theory came in the early 1980s with the development of cosmic inflation theory, primarily by physicists Alan Guth, Andre Linde, and others. Inflation proposes that the universe underwent an exponential expansion during an incredibly brief period, roughly 10 to the power of -36 to 10 to the power of -32 seconds after the initial singularity. During this fleeting moment, the fabric of space-time expanded faster than the speed of light, doubling in size perhaps 100 times or more. This may seem to violate Einstein's special relativity, which states that nothing can travel faster than light, but there's no contradiction. The prohibition against faster-than-light travel applies to objects moving through space, not to the expansion of space itself. During inflation, no object moved through space faster than light, but the space between objects expanded so rapidly that distant regions quickly moved beyond each other's light horizons. Inflation elegantly solves several problems with the original Big Bang theory, including the horizon problem, why the CMB is so uniform when distant regions couldn't have been in causal contact, and the flatness problem, why the universe appears so geometrically flat. It also explains the origin of the large-scale structure in the universe, the vast cosmic web of galaxy clusters and superclusters, as arising from quantum fluctuations in the very early universe that were stretched to cosmic scales by the inflationary expansion. The evidence for inflation has grown stronger over the decades, particularly with precise measurements of the cosmic microwave background by satellites like WMAP and Planck, which have confirmed many of its predictions. However, the underlying mechanism that drove inflation, typically described in terms of a hypothetical field called the inflaton, remains incompletely understood and is an active area of research. What makes the beginning of the universe so conceptually challenging is that it represents not just the origin of all matter and energy, but of space and time themselves. This forces us to confront profound philosophical questions about the nature of beginnings and the limits of causality. If time itself began with the Big Bang, what meaning can we ascribe to the question of what came before? If there was no time, there was no before in any conventional sense. This conundrum has led to various speculative frameworks that attempt to address the question of origins. Some theoretical approaches suggest that our Big Bang might be one event in a larger cosmic context, perhaps a bounce following the collapse of a previous universe in a cyclical model, or a quantum fluctuation in a pre-existing state sometimes called the quantum vacuum, or one bubble universe nucleating within a vast multiverse. Others propose that time as we understand it emerges from a more fundamental timeless reality described by quantum mechanics. The mathematician and physicist Roger Penrose has proposed a model called conformal cyclic cosmology, suggesting that what we perceive as the beginning of our universe might be connected to the far future of a previous cosmic aeon, with the transition occurring when all matter has decayed and the universe has reached a state of maximum entropy. In this model, the absence of any time or length scale in this maximally entropic state makes it physically equivalent to the conditions at the Big Bang, allowing a smooth transition from one aeon to the next. String theory and its extension, M-theory, offer other possibilities, including scenarios where our universe results from the collision of higher-dimensional branes, membrane-like objects, in a higher-dimensional space. Loop quantum cosmology, derived from loop quantum gravity, suggests that the apparent singularity at the Big Bang might be replaced by a big bounce, with quantum gravitational effects preventing infinite density and creating a transition from a contracting phase to an expanding one. What all these approaches share is an attempt to extend our physical understanding beyond the apparent beginning of time itself, to provide a framework where the Big Bang is not an absolute beginning, but a transition or an event within a larger context. Yet they all face the same fundamental challenge: how to formulate meaningful physical theories about conditions where our current understanding of space, time, and physical law breaks down. The question of what, if anything, existed before the Big Bang touches on the limits not just of our physical theories, but of language and thought themselves. Our concepts of existence and causality are temporally structured. We naturally think in terms of before and after, cause and effect. When we reach the boundary where time itself begins, these conceptual tools may become inadequate. As the philosopher Ludwig Wittgenstein might have put it, we may be reaching the limits of what can be meaningfully spoken about within our current conceptual framework. Some physicists and philosophers suggest that the question of what caused the Big Bang or what came before it might be fundamentally misconceived, like asking what's north of the North Pole. Just as the North Pole represents the boundary of the northward direction on Earth's surface, the Big Bang may represent the boundary of temporal concepts in our universe. There is no before the beginning of time in the same way there is no north of the northernmost point. Others argue that while our current theories reach their limits at the Big Bang, this doesn't necessarily mean reality itself has a boundary there. The apparent beginning might reflect the limitations of our current understanding rather than an absolute origin of reality. Future theories of quantum gravity might provide a framework for meaningfully extending our understanding beyond this apparent boundary. The philosophical implications of space and time having a beginning extend beyond physics into realms of metaphysics, theology, and existential thought. Many religious traditions have creation narratives that resonate with the idea of an absolute beginning, though the scientific account differs in its details and explanatory framework. Some see the Big Bang as compatible with the concept of divine creation, while others view it as a purely natural process requiring no external cause. From an existential perspective, the idea that the entire universe, including time itself, had a beginning reminds us of the contingency of existence. The universe as we know it, with all its galaxies, stars, planets, and life, need not have existed. This contingency raises questions about meaning and purpose that science alone cannot answer, but that each of us must grapple with as conscious beings within this vast cosmic tapestry. As our understanding of the early universe continues to evolve, we may develop more refined theories that push our knowledge closer to the very beginning. Gravitational wave astronomy may eventually allow us to hear echoes from the first fraction of a second after the Big Bang. Advanced particle accelerators might recreate conditions closer to the initial singularity, testing theories about the unification of forces. And theoretical advances in quantum gravity may provide a more complete framework for understanding how space and time themselves could emerge from a more fundamental reality. For now, the beginning of the universe stands as both a frontier of scientific understanding and a profound philosophical mystery, a place where our most successful physical theories reach their limits, and where the very concepts we use to make sense of reality may need to be reconsidered or transcended. As we contemplate the cosmic tapestry of space-time, we find that its beginning represents not just an event in the distant past, but a boundary of thought itself, a horizon where science, philosophy, and wonder converge. From the extreme compression of space-time at the Big Bang, let's now turn to a different kind of extreme: the way the fabric of reality behaves when objects approach the cosmic speed limit, the speed of light. From the extreme compression of space-time at the Big Bang, let's now turn to a different kind of extreme: the way the fabric of reality behaves when objects approach the cosmic speed limit, the speed of light. Imagine our cosmic tapestry once again, but now picture yourself moving across it at different speeds. At everyday velocities, walking, driving, even flying in an airplane, the tapestry appears essentially unchanged. But as your speed increases dramatically, approaching significant fractions of light speed, something remarkable happens. The tapestry itself seems to transform. It stretches in some directions and compresses in others, altering your perception of distances and durations in ways that profoundly challenge our intuitive understanding of reality. These relativistic effects, though they may seem like science fiction, have been experimentally verified countless times with extraordinary precision. They represent not merely an abstract mathematical curiosity, but a fundamental aspect of how our universe operates at high velocities. The fact that these effects remain imperceptible in our everyday experience speaks not to their unreality, but to the limited range of speeds we typically encounter in human life. A tiny fraction of the cosmic speed limit of 299,792,458 meters per second, the speed of light in vacuum. The roots of our modern understanding of relativistic space-time lie in Albert Einstein's special theory of relativity, published in 1905. Einstein began with two deceptively simple postulates. First, that the laws of physics are the same for all observers moving at constant velocities relative to each other. And second, that the speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. From these principles, which Einstein believed must be true for electromagnetism to work consistently, he derived a series of consequences that revolutionized our understanding of space and time. The first key relativistic effect is time dilation, the phenomenon whereby time passes more slowly for objects in motion relative to an observer. Imagine a light clock, consisting of a photon bouncing between two mirrors separated by a fixed distance. For an observer at rest relative to this clock, the photon travels straight up and down, marking time with each complete round trip. But for an observer moving relative to the clock, the photon appears to travel a longer, diagonal path as the mirrors move horizontally during the photon's journey. Since the speed of light remains constant for all observers, this longer path means the moving clock must tick more slowly when viewed from the stationary frame. This isn't merely a perceptual effect or an illusion. It represents a genuine difference in the rate at which time passes in different reference frames. The mathematical relationship is described by the Lorentz factor, often represented by the Greek letter gamma, which equals 1/square root 1, v superscript 2 /c superscript 2, where v is the relative velocity and c is the speed of light. As v approaches c, this factor grows dramatically, approaching infinity as v gets arbitrarily close to c. The effects of time dilation become significant only at very high speeds. At 10% of light speed, time slows by only about 0.5%. At 50% of light speed, time runs about 15% slower. But at 90% of light speed, time slows by more than a factor of 2, and at 99% of light speed, time passes more than 7 times more slowly in the moving frame compared to the stationary one. These effects have been confirmed through numerous experiments. Perhaps most directly, atomic clocks placed on commercial airliners have been found to run slightly slower than identical clocks left on the ground, exactly as predicted by special relativity. Even more dramatically, subatomic particles called muons, which are created in the upper atmosphere by cosmic rays, should decay so quickly that very few would reach Earth's surface. Yet we detect them in abundance because, from our perspective, their extremely high velocities cause their internal clocks to run much slower, extending their lifetimes and allowing them to reach detectors on the ground. The second key relativistic effect is length contraction, the phenomenon whereby objects appear shortened in their direction of motion when viewed by an observer relative to whom they are moving. Just as with time dilation, this effect is governed by the Lorentz factor, with an object of proper length L appearing to have a contracted length of L equals L/gamma when viewed from a reference frame in which it is moving at velocity v. To understand why this occurs, consider that if time runs slower in a moving reference frame and the speed of light remains constant for all observers, then distances must contract to maintain consistency. If a moving observer measures the same speed of light as a stationary observer, but their clock runs slower, then they must measure a shorter distance for light to travel to maintain the same calculated speed. The third fundamental relativistic effect is the relativity of simultaneity. The fact that events that appear to occur simultaneously to one observer may occur at different times according to another observer moving relative to the first. This directly challenges our intuitive notion that there exists a universal now that all observers would agree upon, regardless of their state of motion. To visualize this, imagine a train moving at relativistic speed along a straight track. Lightning strikes both the front and rear of the train, leaving marks on both the train and the track. An observer standing on the platform midway between the marks on the track sees both lightning bolts simultaneously, as the light from each strike reaches them at the same time. But a passenger standing in the middle of the train has a different experience. Since the train is moving forward, the light from the strike at the rear of the train has a shorter distance to travel to reach the passenger, while the light from the front strike has a longer journey. The passenger therefore sees the rear strike before the front one. The crucial insight is that neither observer is wrong. Their disagreement about the timing of the events reflects a fundamental property of space-time itself, not a mistake or illusion. In Einstein's framework, simultaneity is not absolute, but relative to the observer's reference frame. These three effects, time dilation, length contraction, and the relativity of simultaneity, combine to create a picture of space-time that differs radically from our intuitive Newtonian understanding. In Newton's view, space and time were absolute and independent, a universal stage upon which the drama of physics played out. In Einstein's relativistic framework, space and time are revealed as aspects of a unified four-dimensional continuum called space-time, with the experience of space and time depending on the observer's state of motion. Perhaps the most famous thought experiment illustrating these relativistic effects is the twin paradox. Imagine identical twins, one of whom remains on Earth while the other embarks on a journey to a distant star at relativistic speed. According to special relativity, the traveling twin's clock runs slower from the earthbound twin's perspective. When the traveling twin returns to Earth, they will have aged less than their sibling. This seems to create a paradox. From the traveling twin's perspective, couldn't they consider themselves stationary and the Earth moving away and then returning, meaning the earthbound twin should be younger? The resolution lies in recognizing that the traveling twin's reference frame is not inertial throughout the journey. They must accelerate to turn around and return to Earth. This acceleration breaks the symmetry between the twins' experiences, resolving the apparent paradox. The traveling twin really does age less, a physical effect that would be measurable with precise enough clocks. These relativistic effects fundamentally challenge our intuitive understanding of reality. Our everyday experience leads us to think of space and time as separate, absolute quantities, with a universal now that all observers would agree upon. Relativity reveals this intuition to be merely an approximation valid at the low velocities we typically encounter. At speeds approaching that of light, the fabric of reality behaves very differently than our intuition suggests. One of the most profound philosophical implications of special relativity is its suggestion that past, present, and future may all exist equally in a four-dimensional block universe. In this view, time is not fundamentally different from the three spatial dimensions. It is simply another coordinate in a four-dimensional space-time continuum. Our perception of a flowing now moving from past to future might be a psychological construct rather than a fundamental aspect of reality. The physicist Hermann Minkowski, who formalized the mathematics of four-dimensional space-time, expressed this view eloquently. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. In this perspective, all events, past, present, and future, exist equally in the four-dimensional tapestry of space-time. Our consciousness simply traces a path through this tapestry, experiencing it sequentially. This block universe view raises profound questions about determinism and free will. If the future already exists in some sense, does this mean our choices are predetermined? Or is there still room for contingency and choice within this framework? Philosophers and physicists continue to debate these questions with no clear consensus. The relativistic nature of space-time also has practical implications for our technology and understanding of the cosmos. GPS satellites must account for both special and general relativistic effects to provide accurate positioning. The study of distant cosmic objects must consider how relativistic effects alter our observations. And any future interstellar travel would need to reckon with the time dilation that would make the journey very different for travelers compared to those left behind. Special relativity also sets a cosmic speed limit, the speed of light in vacuum, that appears to be insurmountable for any object with mass. As an object with mass accelerates, its energy increases according to Einstein's famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light. As the velocity approaches the speed of light, the energy required for further acceleration approaches infinity, making it impossible to reach or exceed light speed. This cosmic speed limit has profound implications for our dreams of interstellar travel and communication. The nearest star system to our own, Alpha Centauri, lies about 4.37 light-years away. This means that even traveling at the speed of light, which is impossible for objects with mass, it would take more than 4 years to reach it. Any signal we send to potential civilizations around other stars would take years, decades, or even centuries to arrive, with an equal delay for any reply. The vast distances of space, combined with the cosmic speed limit, create a fundamental isolation between star systems that no foreseeable technology can fully overcome. Yet special relativity, with all its counterintuitive implications, represents only part of Einstein's revolutionary reconceptualization of space-time. His general theory of relativity, published a decade after special relativity, extended these insights to incorporate acceleration and gravity, revealing that the fabric of space-time is not merely affected by high-speed motion, but can be curved by mass and energy. This curvature manifests as the force we experience as gravity, linking the very large, cosmic structure with the very fast, relativistic effects in a unified geometric framework. As we contemplate how motion affects the fabric of space-time, let's now consider regions where this fabric appears to have a different structure altogether. The mysterious dark energy that seems to be intrinsic to space itself, driving the accelerating expansion of our universe and potentially determining its ultimate fate. As we delve into the mysteries of the universe, we must confront one of the greatest enigmas of modern cosmology: dark energy. This unknown force is not merely a figment of theoretical speculation. It represents a fundamental aspect of our universe that has profound implications for its future. Dark energy appears to be woven into the very fabric of space-time itself, acting as a kind of cosmic tension that causes the expansion of the universe to accelerate. Imagine a grand tapestry that not only stretches as it expands, but also generates its own threads as it unfolds. This analogy captures the essence of dark energy and its role in shaping our cosmos. The story of dark energy begins in the late 1990s when astronomers made a startling discovery while studying distant supernovae. These supernovae, which serve as standard candles for measuring cosmic distances, were expected to show that the expansion of the universe was slowing down due to the gravitational attraction of all matter. Instead, the data revealed a surprising trend. Distant supernovae were fainter than expected, indicating that they were further away than they should be if the expansion were decelerating. This unexpected observation suggested that the universe's expansion was not only continuing, but actually speeding up. The realization that the universe is accelerating in its expansion was a revolutionary moment in cosmology, leading to the introduction of dark energy as a necessary component of our understanding of the universe. This mysterious force seemed to counteract the attractive effects of gravity, providing a repulsive effect that drove galaxies apart. The implications of this discovery were staggering. If dark energy exists and constitutes approximately 68% of the total energy content of the universe, then the familiar framework of cosmology needed to be fundamentally reconsidered. The leading theoretical explanation for dark energy is that it may represent the energy of the vacuum itself, an intrinsic property of empty space. This idea aligns with the concept of the cosmological constant, which Einstein originally introduced in 1917 as a way to achieve a static universe. After the discovery of the expanding universe, Einstein abandoned the cosmological constant, calling it his greatest blunder. Yet, in light of the accelerating expansion, this constant has returned to the forefront of cosmological theories. The cosmological constant implies that even in the absence of matter, space itself possesses energy. This energy density is thought to remain constant as the universe expands, unlike matter and radiation, which dilute as they spread out. As the volume of the universe increases, the energy associated with dark energy does not diminish, thus driving the acceleration of cosmic expansion. This concept is astonishing because it suggests that the very fabric of space-time is dynamic and active, filled with energy that influences the universe's fate. However, dark energy is not without its challenges. One of the most perplexing issues in modern physics is the cosmological constant problem. According to quantum field theory, the vacuum should contain enormous energy densities due to quantum fluctuations, resulting in a cosmological constant value that is many orders of magnitude larger than what we observe. This discrepancy between theoretical predictions and observational evidence is one of the most significant unsolved problems in physics, leading to questions about our understanding of both quantum mechanics and gravity. The implications of dark energy for the fate of the universe are profound and unsettling. Current observations suggest that the universe will continue to expand forever at an accelerating rate. This scenario leads to a future often described as cosmic loneliness. Over billions of years, galaxies beyond our local group will recede beyond the cosmic event horizon, becoming invisible to us as their light fades from view. The universe will grow increasingly empty, with only a few galaxies remaining, and eventually, all stars will burn out, leaving behind a dark and cold cosmos. This vision of an eternally expanding universe raises philosophical questions that resonate deeply with our human experience. What does it mean to live in a universe that will eventually become dark and lifeless? How do we find purpose and meaning in a vast, ever-expanding cosmos that may ultimately lead to isolation? These questions reflect the existential dilemmas faced by humanity as we grapple with our place in the universe and the inevitability of cosmic change. Dark energy also presents challenges to our understanding of fundamental physics. The fact that its observed value is so much smaller than theoretical predictions suggests that our current theories are incomplete. This discrepancy invites speculation about the nature of dark energy. Is it a fundamental aspect of the universe, or is it an emergent phenomenon arising from more basic principles? Some researchers propose that dark energy might be a dynamic field, changing over time, rather than a constant. The exploration of dark energy has led to various theoretical frameworks that attempt to explain its properties. One such approach is quintessence, which posits that dark energy is a dynamic scalar field that evolves over time. Unlike the cosmological constant, which remains fixed, quintessence would allow for variations in the energy density of dark energy, potentially leading to different cosmic scenarios. This concept introduces a level of complexity that could help resolve some of the contradictions in our current understanding. Another possibility is that dark energy could be a manifestation of modifications to gravity at cosmic scales. Some theories propose that our understanding of gravity needs to be adjusted at large distances to account for the observed acceleration of the universe. These modifications could provide alternative explanations for dark energy, offering insights into the unification of general relativity and quantum mechanics. As we explore the implications of dark energy for the universe, we must also consider its impact on our understanding of cosmic evolution. The presence of dark energy suggests that the universe is moving toward a future dominated by empty space, a scenario that challenges our perception of how the cosmos evolves over time. In this view, the grand structures we see today, galaxies, clusters, and superclusters, will eventually dissipate, leaving behind a vast, cold expanse where the rich complexity of the universe once thrived. Yet even in this seemingly desolate future, the legacy of dark energy will remain. It has shaped the structure and evolution of the universe, influencing the formation of galaxies and stars. Dark energy's role in cosmic expansion creates a dynamic interplay with gravity, leading to the formation of large-scale structures like galaxy clusters, superclusters, and cosmic filaments. Without dark energy, the universe would likely have collapsed back on itself long ago, preventing the formation of the rich tapestry of cosmic structures we observe today. As we continue to explore dark energy, we may uncover more about its mysterious nature and implications. Future observations of distant supernovae, galaxy clusters, and the cosmic microwave background may provide further insights into the properties of dark energy and its role in cosmic evolution. Additionally, advancements in theoretical physics may lead us to a deeper understanding of the fundamental principles governing our universe. As you contemplate these vast cosmic processes, consider that the space around you is not static, but is instead filled with the dynamic energy of dark energy, shaping the universe's fate even as you rest. The very fabric of space-time is imbued with this mysterious force, influencing everything from the formation of galaxies to the ultimate destiny of the cosmos itself. While dark energy represents a mysterious property of the cosmic fabric on the largest scales, let's now explore equally mysterious structures that might exist on the smallest scales, the possibility that extra dimensions are folded into the tapestry of reality. These hidden dimensions may reveal even deeper truths about the nature of existence and the fundamental structure of the universe. While dark energy represents a mysterious property of the cosmic fabric on the largest scales, let's now explore equally mysterious structures that might exist on the smallest scales, the possibility that extra dimensions are folded into the tapestry of reality. Imagine for a moment an ant crawling along a garden hose stretched across a yard. To the ant, the hose appears as a one-dimensional path, a line extending forward and backward. The ant can move along the length of the hose, but perceives no other direction of travel. Yet we, from our perspective, can clearly see that the hose has a second dimension, its circular cross-section. The ant could, in principle, walk around the circumference of the hose. But if that circumference were small enough compared to the ant's size, this circular dimension would remain imperceptible to it. This simple analogy captures the essence of how our universe might contain additional spatial dimensions beyond the three we experience daily. We move freely through length, width, and height, but there could be other dimensions so tightly curled or compactified that they remain hidden from our everyday perception. These extra dimensions wouldn't be located elsewhere, but would exist at every point in our familiar three-dimensional space, just as the circular dimension of the hose exists at every point along its length. The concept of extra dimensions has a rich history in theoretical physics, dating back to the early 20th century, when Theodore Kaluza and Oscar Klein independently proposed that our universe might contain a fourth spatial dimension. Their goal was to unify electromagnetism with Einstein's theory of gravity by embedding both forces in a five-dimensional spacetime, four spatial dimensions plus time. Although this particular approach didn't ultimately succeed, it established a powerful paradigm that phenomena appearing distinct in our observable world might be unified when viewed from a higher dimensional perspective. This paradigm found its most comprehensive expression in string theory, which emerged in the late 1960s and developed through subsequent decades. String theory proposes that the fundamental building blocks of reality are not point-like particles, but tiny, one-dimensional strings that vibrate in different patterns. These vibration patterns determine the properties of the particles we observe, much as different vibration patterns on a violin string produce different musical notes. For string theory to be mathematically consistent, however, it requires additional dimensions beyond our familiar three spatial dimensions and one time dimension. Different formulations of string theory suggest different numbers of dimensions, typically 10, 9 spatial dimensions plus time, or 11 for M theory, a more general framework that unifies various string theories. Some earlier versions even suggested 26 dimensions, though these have largely been superseded by more refined models. Why don't we perceive these extra dimensions? According to string theory, all but our familiar three spatial dimensions are compactified, curled up into incredibly tiny structures at every point in space. The scale of these compact dimensions would be approximately the Planck length, about 10 to the power of -35 meters, far smaller than anything we can directly observe with current technology. At this scale, quantum effects dominate, and the very nature of space becomes granular and exotic. The geometry of these hidden dimensions is not arbitrary. String theorists propose that they form specific mathematical structures called Calabi-Yau manifolds, complex, six-dimensional shapes with particular properties. The precise configuration of these manifolds would determine fundamental aspects of our universe, including the types of particles that exist, their masses, and the forces through which they interact. Different Calabi-Yau configurations would yield different physical laws, potentially explaining why our universe has the specific properties we observe. This connection between the geometry of hidden dimensions and the physics of our observable world represents one of the most profound insights of string theory. It suggests that the seemingly arbitrary constants and parameters of particle physics, the masses of elementary particles, the strengths of fundamental forces, might actually be determined by the shapes and sizes of compact dimensions beyond our perception. What appears as a complex zoo of particles and interactions in our three-dimensional experience might emerge naturally from a more elegant, higher-dimensional reality. Another influential framework involving extra dimensions is the Randall-Sundrum model, proposed by physicists Lisa Randall and Raman Sundrum in 1999. This model suggests that our universe might be a four-dimensional brane, short for membrane, floating within a higher-dimensional bulk space. In this scenario, most particles and forces would be confined to our brain, explaining why we don't perceive the extra dimensions. Gravity, however, would be able to leak into the bulk, potentially explaining why gravity appears so much weaker than the other fundamental forces. This weakness of gravity compared to the other forces, the electromagnetic, strong nuclear, and weak nuclear forces, represents one of the great puzzles in physics, known as the hierarchy problem. Why is gravity approximately 10 to the power of 36 times weaker than the electromagnetic force? In the Randall-Sundrum framework, gravity might appear weak in our brain because much of its strength is dissipated into the extra-dimensional bulk. From this perspective, gravity isn't intrinsically weaker than the other forces. It just seems that way because we're experiencing only a fraction of its total strength. The concept of branes extends beyond the Randall-Sundrum model. In some versions of string theory, our universe might be one of many branes floating in a higher dimensional bulk. These branes might occasionally collide, with such collisions potentially explaining cosmic events like the Big Bang. This brane cosmology offers alternative perspectives on the origin and evolution of our universe, suggesting that what we perceive as the beginning of everything might actually be a collision or interaction between higher dimensional structures. Hidden dimensions might also help explain other cosmic mysteries, such as dark matter, the invisible substance that appears to make up about 85% of the matter in the universe. Some theories propose that dark matter particles might be able to travel through extra dimensions, taking shortcuts through higher dimensional space. This could explain why dark matter interacts so weakly with ordinary matter and why it has proven so difficult to detect directly. Other theories suggest that dark matter might consist of particles that are confined to other branes, interacting with our brain primarily through gravity. The concept of extra dimensions also plays a crucial role in addressing one of the most profound questions in cosmology. Why does our universe appear fine-tuned for life? The fundamental constants of nature, the strength of gravity, the mass of the electron, the strength of the nuclear forces, all seem calibrated with extraordinary precision to allow for the existence of stable atoms, stars, and ultimately, life. If any of these constants were slightly different, the universe would be incapable of supporting complexity. One explanation for this apparent fine-tuning emerges from the landscape of possible universes suggested by string theory. If the specific configuration of extra dimensions determines the physical laws in our observable universe, and if many different configurations are possible, then there might exist a vast multiverse of universes, each with different physical laws. Most of these universes would be inhospitable to life, but we necessarily find ourselves in one of the rare universes capable of supporting our existence. This anthropic reasoning doesn't explain why the multiverse exists, but it could explain why we observe a universe with life-permitting properties. While these theoretical frameworks are mathematically elegant and offer potential solutions to long-standing problems in physics, they remain speculative. No direct experimental evidence for extra dimensions has yet been found, though physicists have proposed various ways they might be detected. One approach involves searching for deviations from Newton's law of gravity at very small distances, where the effects of extra dimensions might become apparent. Another involves looking for signatures of extra dimensions in high-energy particle collisions at accelerators like the Large Hadron Collider. Some theorists have also suggested that certain astronomical observations might provide indirect evidence for extra dimensions. For instance, if gravity can leak into extra dimensions, this might affect the gravitational waves produced by cosmic events like black hole mergers. Precise measurements of these waves might reveal subtle discrepancies from predictions based on conventional four-dimensional spacetime. The concept of hidden dimensions challenges our intuitive understanding of reality in profound ways. We naturally think of space as three-dimensional because that's what our senses perceive. But our senses evolved to navigate the macroscopic world, not to perceive the fundamental nature of reality at its smallest scales. Just as our eyes cannot see infrared or ultraviolet light without technological assistance, our spatial perception might be limited to three dimensions even if reality contains more. This limitation of our perceptual apparatus raises philosophical questions about the relationship between appearance and reality. If our universe contains dimensions beyond our direct experience, what other aspects of reality might lie beyond our perception? How much of what we consider fundamental to our understanding of the world is shaped by the specific ways we interact with it? These questions echo ancient philosophical inquiries about the nature of reality versus appearance, but framed in the context of modern theoretical physics. The possibility of hidden dimensions also transforms our understanding of our place in the cosmos. If our universe is a brain floating in a higher dimensional bulk, potentially alongside other brain universes, then the totality of reality might be vastly more complex and diverse than we have imagined. Our universe, with its billions of galaxies and trillions of stars, might be just one manifestation of a much larger multiverse structure, much as our planet is just one of many in our solar system. This perspective invites both humility and wonder. Humility, because it suggests that what we can directly observe and measure might be just a small slice of a much grander reality. Wonder, because it points to the extraordinary richness and complexity that might lie beyond our immediate perception, waiting to be discovered through the combined tools of mathematics, theoretical physics, and eventually, perhaps, direct experimental evidence. As we continue to explore these possibilities, we remain at the frontier of human understanding, pushing the boundaries of what we can conceive and potentially discover about the fundamental nature of reality. The concept of hidden dimensions reminds us that the universe might be not only stranger than we imagine, but stranger than we can imagine, a tapestry of reality with layers and structures beyond our everyday experience, but potentially accessible through the power of mathematical physics and experimental ingenuity. As you contemplate these hidden dimensions potentially folded into every point of the space around you, Consider that what appears as empty void might actually contain intricate geometric structures at scales too small to perceive directly. The room around you, your own body, and indeed the entire observable universe might be embedded within a higher dimensional reality that shapes and constrains the physics we experience. This perspective transforms our understanding of space itself, suggesting that what we perceive as three-dimensional might be a projection or slice of a more complex dimensional structure. As we contemplate dimensions beyond our perception folded into the cosmic fabric, let's conclude by considering the ultimate question about space-time, whether it is a fundamental aspect of reality or perhaps an emergent property arising from something even more basic. A final twist in our exploration of the cosmic tapestry that might reframe everything we've discussed so far. As we contemplate dimensions beyond our perception folded into the cosmic fabric, let's conclude by considering the ultimate question about space-time, whether it is a fundamental aspect of reality or perhaps an emergent property arising from something even more basic. Throughout our exploration of the cosmic tapestry, we've treated space-time as the fundamental arena in which all physical processes occur, the stage upon which the drama of the universe unfolds. But what if space and time themselves are not primary, but secondary, not the canvas, but rather patterns painted by deeper, more fundamental processes? This question represents one of the most profound frontiers in theoretical physics, challenging our most basic assumptions about the nature of reality. Consider how we understand temperature. We experience it directly as heat or cold, and it seems like a basic property of matter. Yet physicists know that temperature is actually an emergent phenomenon. It arises from the collective motion of countless atoms and molecules, though no individual particle has a temperature. Temperature describes the average kinetic energy of a collection of particles, a statistical property that emerges only at the macroscopic level. Similarly, various cutting-edge theories suggest that what we experience as continuous, flowing space-time might emerge from deeper quantum processes or structures that themselves exist in a framework where our familiar notions of space and time don't apply. In this view, space-time would be like temperature, a useful and very real description of collective behavior that nonetheless isn't fundamental but emerges from something more basic. This perspective represents a radical departure from the way we've understood physics since Einstein. General relativity describes gravity as the curvature of space-time caused by mass and energy, treating space-time itself as a dynamic but fundamental entity. Quantum mechanics, meanwhile, typically treats space-time as a fixed background in which quantum fields operate. The tension between these approaches has made it notoriously difficult to reconcile quantum mechanics with gravity, to develop a theory of quantum gravity that would apply in extreme conditions like the center of black holes or the first moments after the Big Bang. If space-time isn't fundamental but emergent, this might offer a path toward resolving this long-standing tension. Rather than trying to quantize space-time directly, treating it as composed of discrete units, we might need to identify the more fundamental structures or processes from which space-time emerges, and then derive both quantum mechanics and general relativity as approximate descriptions that apply in appropriate regimes. Several theoretical approaches have been developed that explore how space-time might emerge from more fundamental structures. One of the most prominent is loop quantum gravity, which suggests that space itself is not infinitely divisible, but composed of discrete units often called atoms of space or spin networks. These fundamental building blocks are not located in space. They are space, with spatial relationships emerging from their connections to each other. In this framework, continuous space is an approximation that works well at scales much larger than these fundamental units, just as the apparently smooth flow of water emerges from the collective behavior of discrete water molecules. Loop quantum gravity describes these atoms of space in terms of quantized volumes, areas, and lengths, with the quantum nature of geometry becoming apparent only at the Planck scale, approximately 10 to the power of -35 meters. At larger scales, these discrete elements blend together to create the apparently continuous spacetime described by general relativity. This approach maintains Einstein's insight that gravity is geometry while incorporating the quantum principle that physical properties are ultimately discrete rather than continuous. Another approach, causal set theory, proposes that the fundamental nature of reality is not spatial or temporal, but causal. In this view, the universe at its most basic level consists of a collection of events and the causal relationships between them, which events can influence which other events. Space-time geometry emerges from this network of causal connections, with distance and duration being derived concepts rather than fundamental ones. The apparently continuous space-time we experience would be an approximation of this deeper causal structure, similar to how a digital image composed of discrete pixels can appear continuous when viewed from a distance. Perhaps the most radical reconceptualization comes from holographic principles, inspired by studies of black hole thermodynamics and string theory. The holographic principle suggests that all the information contained in a volume of space can be encoded on its boundary. Our three-dimensional reality might emerge from information encoded on a two-dimensional surface, much as a hologram creates the illusion of three dimensions from a pattern on a flat surface. The most concrete realization of this principle is the anti-de Sitter/conformal field theory, AD/CFT, correspondence, proposed by Juan Meldacena in 1997. This framework establishes a mathematical equivalence between a theory of gravity in a space with particular properties, anti-de Sitter space, and a quantum field theory without gravity that operates on the boundary of that space. In this correspondence, the higher dimensional gravitational physics emerges from the lower dimensional quantum physics, a striking illustration of how space-time geometry might not be fundamental but emergent from more basic quantum processes. These approaches share a revolutionary implication. Information and the relationships between quantum events may be more fundamental than space and time themselves. Space-time geometry might be a way of organizing information about how quantum systems relate to each other, rather than an independent, primary feature of reality. In this view, the question, where is this quantum of space, makes no more sense than asking, where is this degree of temperature? Both are emergent properties that describe collective behavior, not localized objects. This perspective aligns with growing recognition that information may play a fundamental role in physics. John Wheeler, the physicist who coined the terms black hole and quantum foam, captured this idea in his famous phrase, "it from bit," suggesting that physical reality might ultimately derive from information, bit. If so, space-time might be a way of organizing and expressing relationships between bits of information, rather than a fundamental container in which information exists. The philosophical implications of space and time being emergent rather than fundamental are profound and far-reaching. Our entire conceptual framework for understanding reality is built around space and time. We think of objects as existing at particular locations, events as occurring at specific moments, and causality as operating through space-time connections. If space and time themselves emerge from deeper structures where these concepts don't apply, we may need to radically revise our understanding of existence itself. This perspective challenges our most basic intuitions about reality. We naturally think of reality as unfolding within space and time, with objects having definite locations and events occurring in a specific order. But if space-time is emergent, then at the most fundamental level, reality might not be spatiotemporal at all. Our perception of a continuous, flowing space-time might be a kind of illusion, not in the sense of being unreal, but in the sense of being an approximation that works well for our macroscopic experience while breaking down at the most fundamental level. This would be similar to how Newtonian physics provides an excellent approximation of reality at everyday scales and speeds, but breaks down in extreme conditions, where Einstein's relativity becomes necessary. Similarly, our entire spatiotemporal framework might be an approximation that works well for most purposes, but fails to capture the true nature of reality at its most fundamental level. If space and time are emergent rather than fundamental, this might help resolve some of the deepest paradoxes in physics. The conflict between quantum mechanics and general relativity might be resolved not by finding a way to combine them directly, but by recognizing that both are approximate descriptions emerging from a more fundamental theory where neither quantum fields nor space-time geometry are primary. The puzzle of quantum entanglement, where particles can maintain instantaneous connections regardless of distance, might be explained if space itself is not fundamental but emerges from relationships between quantum systems. In this view, entangled particles might be directly connected at the pregeometric level from which space emerges, making their apparently spooky action at a distance less mysterious. Similarly, the information paradox of black holes might find resolution if space-time and the information it contains both emerge from more fundamental structures. The apparent destruction of information when matter falls into a black hole might be an artifact of our space-time description rather than a fundamental problem, with information preserved in the deeper structures from which space-time emerges. The emergence of space-time might also shed light on the origin of the universe. If space and time themselves are not fundamental but emergent, then the Big Bang might not represent the beginning of everything, but rather the emergence of space-time from a more fundamental reality that itself had no beginning in the conventional sense. The question, what happened before the Big Bang, might be revealed as misconceived, not because time began at the Big Bang, the conventional answer, but because the concept of before only makes sense within already emerged space-time. These perspectives invite us to reconsider philosophical questions about the nature of reality that have been debated since ancient times. The pre-Socratic philosopher Parmenides argued that change and multiplicity are illusions, and that reality is an unchanging, undivided whole. Eastern philosophical traditions like Advaita Vedanta similarly suggest that the apparent diversity and separation we perceive masks a deeper, unified reality. While these ancient insights were not formulated in the language of modern physics, they resonate with the possibility that our perception of a world of separate objects existing in space and time might be an approximation of a deeper reality where such distinctions dissolve. The question of whether space-time is fundamental also connects to ongoing debates about the role of mathematics in describing reality. If space-time emerges from more abstract mathematical structures, this might suggest that mathematics is not merely a human tool for describing reality, but somehow more directly connected to the fundamental nature of existence. The physicist Eugene Wigner famously wrote about the unreasonable effectiveness of mathematics in the natural sciences, the puzzling fact that abstract mathematical structures often turn out to describe physical reality with extraordinary precision. If reality at its most fundamental level is mathematical rather than spatio-temporal, this effectiveness might seem less mysterious. As we continue to explore these profound questions, we should remember that our theories remain works in progress. The various approaches to quantum gravity and emergent space-time are still being developed, with no clear consensus on which, if any, correctly describes reality. The ultimate answer might incorporate elements from multiple frameworks or emerge from entirely new insights we haven't yet conceived. What seems increasingly clear, however, is that our intuitive understanding of space and time as the fundamental arena of reality may need revision. The journey toward understanding the true nature of reality may require us to transcend our spatio-temporal intuitions, much as earlier scientific revolutions required transcending the intuition that the Earth is stationary or that time flows at the same rate for all observers. As we conclude our journey through the fabric of space-time, from the cosmic tapestry that curves around massive objects to the quantum foam that may underlie reality itself, we're left with more questions than answers. Perhaps that is the nature of true understanding, not to arrive at final certainty, but to deepen our appreciation for the mystery. As you drift toward sleep, imagine yourself floating in this cosmic fabric, connected to all things across space and time through the intricate weave of reality. The universe is not just something we observe. We are part of its tapestry, threads in the grand cosmic design, both observing and embodying the wonder of existence. The space around you, the time through which you move, the very fabric of reality that seems so solid and certain, all may be emergent patterns arising from deeper structures beyond our direct perception. Yet this doesn't make them less real or meaningful. Just as the wetness of water is no less real for emerging from molecules that are not themselves wet, the space-time we experience is no less significant for potentially emerging from something more fundamental. In this light, our exploration of the cosmic tapestry becomes not just a scientific journey, but a philosophical one, an invitation to reconsider the nature of reality itself and our place within it. Whether space-time proves fundamental or emergent, the universe remains a source of wonder and mystery, inviting us to continue our exploration with both rigorous analysis and open-minded humility before the profound questions that remain unanswered.